Okay, here we go. Got some background music here from Little Soul on YouTube. Thanks for the funky lo-fi, relax, stress relief. Well, today we're going to talk about the letter R specifically. It's the correlation coefficient, and we're going to be looking at how to understand the properties of R, as well as how to use R to one's advantage. What can we read from R? All right. First of all, the variable R in statistics is known as the correlation coefficient. It varies between -1 and +1. It's strong when it's on either end, when it's close to -1 and 1, and it's weak in the middle, so when we're close to 0. So it tells us two things. It tells us direction. Remember yesterday we talked about positive and negative, whether we're going up or down. So we might make those little two notes. And then it tells us, obviously, the strength of the relationship between the two variables. So here are some examples. Here's a case of R being -1. Notice how all the dots are lining up exactly in a line. Notice as the explanatory variable increases, the response variable decreases. So that's why it's negative. Here's again another -1, not quite as strong. So the R value there is 0.9. Here we have an R value of approximately -0.536. You won't have to be able to calculate those values. We'll use software, computer website, and or your calculator will tell it to you too. So here we have a data set. R is not given to us. You might suspect here that the R value is like confusing. We can't tell. Is this going up? Is it going down? So therefore we say an R value of 0. Okay, would be a good guesstimate. And we'll change that equals to an approximate. And hopefully you get a chance here to estimate on this one. Go ahead and guess to yourself, what is the R value of the explanatory relationship to the response variable? And hopefully you can see that it's going in an upward direction. It's kind of not exactly lining up into a straight line, so maybe 0.8 or 0.7 maybe, I don't know, somewhere in there. Certainly not a 1. And here we can see we clearly have a +1. They're all lining up nicely, straight line in an upward direction. Okay? We've got to be careful when we interpret here. Here we have elevation versus mean annual temperature in Nevada. So as the elevation increases, our mean temperature is decreasing. And so we can see that the R value is going to be a negative number. In this case, negative maybe 0.9, or maybe 0.8 would be even a better one, because we see that there's actually kind of a separation of values here. And in this case here, again, IQ score versus height, R values all over the place. It's 0. Now, as we use and interpret R, we need to pay attention to 4 things. Number 1, never grab the R value without looking at the graph. We need to make sure that we have a linear relationship, because you could have an R value of 1 and it could be a curve that fits nicely, and so we just don't want to make that assumption. Number 2, are there outliers which are affecting the R value which you're not aware of? So again, we take a look at the picture, and here you have a case of an outlier causing a huge change on that R value. So that which was approximately 0.9 has now changed by 1 variable to be rather poor. But who knows, that outlier may be a bad piece of data. So be careful of outliers, and then sample size. If there's only a few things being graphed and related, then we need to be wary of how much we can rely on that. Like, really, you've only got 7 pieces of data. So getting as much data as possible, and here we get another piece of data, we can get an even stronger relationship. Finally, we don't know what the relationship is between the 2 data sets in, for example, this one here. We don't know, we don't have any axes labels. So we've got to pay attention to homogeneous, meaning the same. Are the 2 variables that we're looking at like similar concepts? Maybe like letter grade and the percentage, right? If I look at those 2 things, the higher your percentage, the larger your letter grade, right? And so those would be like the same thing. So we've got to be careful when we interpret the R value. Finally, even when we've looked at all those things, we must be careful at looking at cause and effect. Item number 1, we never know when there is a lurking variable. What is a lurking variable? It's a creepy variable. It's one which is hidden, and we don't necessarily see it. So here's a couple of examples. Number of firefighters versus the damage caused at a fire. When we look at, some building going up in flames because of a fire, then we look at how many firefighters show up versus how much damage is caused. And in general, the more the firefighter shows up, the more damage is caused. So we were wondering, like, do the firefighters cause the damage? That could be a kind of a causation thing that we put together. But the lurking variable here would be like, how big is the fire? How severe is the fire? If it's a large fire, obviously that's why we call a lot of firefighters. So we've got to be careful about other variables that are hiding. Here's a really weird one: ice cream consumption and the number of crimes that are committed. So as we consume more ice cream, then there are more crimes being committed out in the world. And we wonder, well, why is this? Is there something bad about ice cream? And the answer is no. There is a hidden variable. I don't know if you know what that is in this case. The lurking variable is temperature, meaning as it gets warmer during the summer, then we eat more ice cream. But we also go outside and we brush up against people, and sometimes we get a little upset, and then people get angry, and the next thing you know, there's crime. There's shooting in the streets. Just kind of kidding, there isn't that serious. But crimes do increase over the course of the summer. It doesn't have to do necessarily with ice cream, but rather a hidden variable of having more time and being outside. Finally, the other thing that we have to be careful is there may be a confounding situation going on. Okay, I should cross off the word variable. There's no variable there. It's just confounding situation. And these are causes which don't make sense. You'll see that here in a couple of examples. So, is this lurking or is it confounding? If we can figure out what might cause it, then we would say it's lurking. If we cannot figure it out, then we would say it's confounding. So this is going to take some thinking on your part. Number 1, more police officers, therefore more crime. Are these 2 lurking or are they confounding? Hopefully you are under the assumption that the police officers don't create the crime. Though that is somewhat disputable or disputed even today. But we're going to make a big assumption here that police officers do not cause crime. And so then why does a city which have more police officers end up having more crime? Is that a lurking? Like, can we think of a variable that's hiding there that we're not paying attention to? Or is that like confounding? Like, I don't know. That's a mystery why those two things seem to be tied to each other. Well, hopefully you have thought about it, and if the size of the city, so we would say the population size, is larger, then you obviously would have more police officers. And if you have a population size which is larger, you will have more crime. So that's why we would tend to like see those two things increase and decrease together. Again, one is not causing the other, rather it is a lurking variable, which is population size. All right, car seat usage, you know, those little car seats that they put in for kids to ride around in, versus driving under the influence. These two variables seems to be tied together. That is, the more car seat usage we've seen, the more people are driving under the influence. Now, I don't think it has to do with stress about parents and kids, and then therefore parents drinking because of the stress of kids. Rather, I think this is a scenario which is confounding. We really don't know, at least I can't pin it down to anything, why these two variables increase together. There's a positive relationship. But this one, the first one was lurking variable, population size, whereas this one here is confounding. Okay, we don't really know what's going on. What about teen cell phone use versus drug abuse? Teen cell phone use versus drug abuse. Well, clearly, as teen cell phone use has increased, drug abuse increases as well. Again, we wonder, does one cause the other? Right? Is this a cause and effect? There are some people who sit around on their lawn chairs saying, "Get off my lawn," who firmly believe that. Most of us, though, who would tend to agree that no, cell phone use does not create drug abuse. It might possibly enable drug abuse because you can contact people more quickly from all sorts of corners of the world. But I would say for most of us, we would say there is there's a lurking variable here, and that might be something like it's not the use of the cell phone, but the actual that there's a common technology, that technology has advanced. And so drug abuse has also advanced. And we've gotten better at detecting drug abuse. Okay? So the various technological advances would be a possible explanation here. In the past, we weren't aware of drug abuse that was going on because it was hidden, because it wasn't reported, all those things. And I think now we tend to see that more. But it, again, isn't necessarily caused by the cell phone. All right. Well, there we go. Today, correlation coefficient R. It goes between -1 and 1, and you're interpreting those values. Tomorrow we'll start to use R. In fact, I kind of talked about this already. Slope is something that comes up in our discussion of R. So, best of luck as you do your homework in 6-2.